All right, today we're diving into something pretty mind-bending. It's a quantum algorithm that could completely flip the script on how we find, well, anything. It's called Grover's algorithm. And really, it represents a leap in search power that's kind of like going from a bicycle straight to a rocket ship. So, let's get into it. Okay, so let's start with a puzzle. Picture this. You've got a massive phone book, but it's a total mess. A billion names, completely random, totally unsorted. Now, how would you go about finding one specific name in that chaos? It sounds simple, right? But this exact problem is actually one of the biggest headaches in all of computing. And it's really at the core of what we're talking about today. You know that whole phone book scenario? It's not just some random thought experiment. It's a real thing, and it's called the universal search problem. Basically, finding one specific needle in a giant, disorganized haystack, a huge, unstructured database, is a massive, massive challenge for the computers we all use every single day. So how would a normal computer, what we call a classical computer, tackle this problem? Well, it does it the old-fashioned way. It's called a linear search, and it's exactly what it sounds like. It starts at the very beginning, page 1, name 1. Is this it? Nope. Okay, on to the next one. And the next, and the next. You get the idea. It's super tedious, but hey, it gets the job done, eventually. And right there, that's the big problem. That's the core limitation of a classical search. The time it takes is directly tied to how much stuff you have to look through. So if you have n items in your list, in the worst case scenario, it's going to take you n checks to find what you're looking for. A million items? That could mean a million checks. And with the massive databases we use for everything today, this becomes a huge, huge bottleneck. Okay, so this is where we need a totally different way of thinking, a whole new approach. And that's where quantum computing comes in. See, a quantum computer doesn't just play by the old rules faster. Nope, it uses a completely different rulebook, one that's borrowed from the seriously strange and wonderful world of quantum physics. And it uses those rules to solve certain problems, well, a lot faster. So the most basic piece of a regular computer is the bit, right? It can be a 0 or it can be a 1. That's it. Simple. But a quantum computer uses something called a qubit. And a qubit, well, it can be a 0, it can be a 1, or, and this is the absolute game changer, it can be both at the exact same time. It's this wild ability to exist in multiple states at once that lets a quantum computer check a whole bunch of possibilities all at the same time. This amazing property has a name. It's called superposition. And probably the best way to wrap your head around it is to think of a spinning coin. While that coin is spinning in the air, is it heads or tails? Well, it's neither, and it's also kind of both. It's in a state of all possibilities at once. It's only when it finally lands, or in our case, when we measure the qubit, that it picks a side and collapses into a single definite state. This one idea is really where quantum computing gets its incredible power. Okay, so how do we actually use these weird quantum rules to solve our search problem? How do we find that one name in the giant, messy phone book? Well, back in 1996, a computer scientist named Love Grover figured it out. He came up with an algorithm that uses superposition to create a kind of quantum shortcut. It lets you find one item in a huge, unsorted list way, way faster than any classical computer ever could. Now, Grover's algorithm basically has two key parts, two secret ingredients. The first one is something called the oracle. The best way to think of the oracle is like a magic judge. It doesn't know where the right answer is, but it knows what the right answer looks like. So when it stumbles across the item we're searching for, it doesn't shout it out. It just flags it. It puts a kind of invisible tag on it for the next step of the process. And that brings us to the second secret ingredient, amplitude amplification. This is what happens after the oracle marks the correct answer. This process takes that marked answer and dramatically boosts our chances of actually finding it. The radio analogy here is perfect. It's like you're tuning an old radio and you hear a faint signal of the song you want. Amplitude amplification is like turning the volume way up on that one station while turning all the other static and noise way, way down. All right, so here's how the whole magic trick works. Step 1, you take all the possible answers, every single name in that phone book, and you put them all into superposition at once. Then the algorithm starts a loop. The oracle goes in and marks the correct answer, then amplitude amplification comes in and boosts it, making it stand out. You repeat that loop, mark, boost, a very specific number of times. And after you do that, the probability of finding that correct answer becomes so high that when you finally measure the system, the answer you're looking for just pops out. It's almost guaranteed. Okay, so We know it's faster. But the big question is, how much faster are we really talking about here? This is where the numbers start to get absolutely wild. Let's talk about what scientists call the quadratic speedup.
It's actually pretty simple to explain. A classical search, like we said, could take up to n steps for a list of n items. Grover's algorithm, on the other hand, takes about the square root of n steps. Now, for small numbers, that might not sound like a huge deal. But for massive databases, the difference between a number and its square root is, well, it's gigantic.
Let me put this in perspective for you because this is where it really clicks. Imagine searching through 1,000,000 items. A classical computer, in the worst case, needs to make 1,000,000 checks. Grover's algorithm? It needs about 1,000. Now let's go bigger. 1,000,000,000 items. That's 1,000,000,000 checks for a regular computer versus just over 31,000 steps for a quantum computer. The difference isn't just an improvement, it's absolutely staggering.
So this isn't just a cool science experiment or a neat bit of theory. Being able to search this much faster has massive real-world implications across so many different fields. Let's take a look at what this algorithm could actually do for us. I mean, think about healthcare. Doctors could sift through millions of patient records to find someone with a very specific rare disease marker almost instantly. In cybersecurity, it could help us search for dangerous vulnerabilities or even password keys much more quickly. Or how about finance, scanning massive logs of transactions to spot fraud? And in logistics, you could find the single best delivery route out of millions, or even billions of possibilities.
Now, it's also really important that we clear up some common misconceptions here. Let's bust a few myths. Myth number 1, this will break all encryption. Nope, not true. It definitely helps, but current standards like AES 256 are still considered pretty safe. Myth number 2, quantum computers are just faster at everything. Also false. They're amazing, but only for very specific kinds of problems, like this unstructured search we've been talking about. And finally, the myth that they're going to replace the computer on your desk. The reality is they'll work alongside them, like super powerful, specialized tools for tackling the kinds of problems that classical computers just can't handle.
And that really brings us to our final thought for today. What Grover's algorithm gives us is this tool of almost unbelievable power for digging through complexity. It changes the game. So the question it leaves us with is a pretty deep one. If we suddenly have the power to find any needle in any haystack, what should we search for first?